Hey guys, welcome to day 8. This is the last day of the course, so congratulations that you've made it this far. So I'm just going to go over a couple of the problems from the worksheet, and then I'm going to spend the rest of the day talking about the derivative as a function, and I'll explain what that means in a moment. You saw a little bit of it on the worksheet last time. So I'd like to go over numbers 3 and 4 from the worksheet from last time. So I'm going to switch to my document camera and we'll take a look. So yeah, so number 3, you're being asked to compute the derivative of the function. So we have the function f of x is equal to x squared. And I'm asking you to compute the derivative of that function at a couple of different locations using what we called the second limit definition of the derivative. That's like the limit as h goes to 0 and so on. So in part A, I ask you to find f prime of 4. That's the derivative of this function at 4. And I want you to use the second limit definition. So the second limit definition, let's just recall what it says in general. It says in general that f prime of c is the limit as h approaches 0, f of c plus h minus f of c all over h. That's the second limit definition. It's the one that we derived last time. So let's just apply it. So we just have to, use this formula, except obviously c is 4 in this case. So f prime of 4 is going to be the limit as h approaches 0 of f of 4 plus h minus f of 4 all over h. Okay, so we now have to compute what some of these things are, right? So limit as h approaches 0, f of 4 plus h. What is f of 4 plus h? Well, that just means you need to replace, go to this formula and replace the x that you see with 4 plus h. So instead of x squared, it's 4 plus h squared. And then minus f of 4, well, f of 4, that's clearly, if you just plug 4 into this thing, you get 16. So f of 4 is 16 all over h. Okay, so this is an algebraic limit. Technically, you should try plugging in the number, right? Whenever you're trying to evaluate a limit like this, technically, you should just try to plug the number in. But I promise that if you plug in 0 for h in this expression, you will get 0 over 0, which means that we need to simplify the expression and then try again. So how can we simplify this expression? Well, certainly one thing that you can do is multiply out this 4 plus h. Again, remember, 4 plus h is not simply 4 squared plus h squared, right? It means 4 plus h times a copy of itself. That's what 4 plus h squared means. And this has to be multiplied out. So if we do that, 4 times 4 is 16. 4 times h is 4h. H times 4 is 4h again. And then h times h is h squared. And then, of course, we still have that minus 16 at the end, all over h. And yeah, there's some simplification that can be done in the numerator. There are some like terms that can be combined. We have a 16 and a minus 16. So those will just cancel, right? Those go away. What else is going on? Well, let's see. We have an h squared, so let me just copy that. And then we have 4h plus 4h, which is, of course, just 8h. So h squared plus 8h all over h. This is still not simplified enough because if you plug in 0 over h, you still get 0 over 0. There's more simplification to be done. What can be done now is that you can pull out a common factor of h from the two terms in the numerator. So let's go ahead and do that. Limit h approaches 0, h quantity h plus 8. Okay, and then we can do some cancellation, right? This h on top here is going to cancel with this h on the bottom there, leaving us with just the limit as h approaches 0 of h plus 8. And now if we plug in 0 for h, we get something very reasonable, namely we just get 8. So that's the value of the limit, and in turn that's f prime of 4. So the derivative of this function at 4 is 8. Or if you like, the instantaneous rate of change of this function at 4 is 8. Or if you like, the slope of the tangent line to this function at 4 is 8. Okay, so all those things are true. Part B, that was part A. Part B asks you to compute f prime of 5. Okay, so instead of f prime of 4, you're looking at f prime of 5. I'm not going to do the whole thing because the work is identical to this. It's exactly the same, except instead of 4s, you've got 5s, and that will be a 25. And but otherwise, you know, the numbers are a little bit different, but it's pretty much the same problem. I'll skip to the chase. You'll find that f prime of 5 is 10. Okay, which is kind of interesting. And what I point out in part C is that you should be observing a pattern. Okay, you should be observing a pattern. Actually, I think I did an example earlier using another point. Well, never mind. So the pattern that you should be observing, you know, you should have seen that f prime of 4 is equal to 8, and f prime of 5 is equal to 10. You know, I hope that you can see there's a pretty simple relationship between this number and this number, right? The output is just twice the input. So, you know, if you had to guess what's f prime of 6, you'd probably guess 12. And that actually turns out to be true. If you crank through the whole problem, you know, using 6, you'll get 12. And f prime of 7 is 14, and so on. And with this in mind, it's pretty clear that we can generalize this, right? Is it true? Is it always true that f prime of, you know, instead of writing a specific number here, like 4 or 5 or 6, what if I just write, you know, say an x, meaning any number? Is that always going to be twice the number that appears here? Like, is the output always going to be twice the input here? In fact, it will be. And in part C, I ask you to prove it. You know, I'm not going to go over it because basically the entire problem is fully worked out in the answer. I show you the full answer, so you can see the work and look at it carefully there. But if you, well, yeah, maybe I'll do it. Yeah, so let's go ahead and do it. So I'll do it quickly. So limit as h approaches 0. So if you want to compute f prime of x, so this is the derivative at any point x, not the derivative at a specific point like 2 or 3 or 4 or 5 or 6, but the derivative in general. You know, you're going to use the same formula that we used over here, right? It's the same formula, limit as h goes to 0, f of c plus h, and so on. The only difference is that, you know, instead of replacing c with a specific number like 4 or 5 or 6, you're going to replace c with x. Okay. And if you do so, that's what you get. Let's remember that our function is x squared. We're going to need that. So, so what is this? Well, it's the limit as h approaches 0. What is f of x plus h? You know, how do you evaluate that? Well, you know, what you have to do is go to your function over here, which is x squared, and replace the x with x plus h. So instead of x being squared, it's x plus h being squared. So that would be x plus h quantity squared minus f of x. Well, f of x is just x squared all over h. So, you know, if you multiply this whole thing out, you know, that's like x plus h times x plus h minus x squared over h. And, you know, if you multiply out the x plus h times itself, you're going to get x squared plus x times h plus h times x, which is also x times h. So you get like 2 copies of that term. plus h times h, which is h squared, and then finally minus x squared all over h. Now there's some simplification that can be done here. This x squared here is being subtracted from that x squared, so those are gone. But also these two middle terms can be combined. Xh plus xh is just two copies of xh. So what I have in the numerator really, as I said, the x squareds go away. We have two copies of xh, and then of course we have the h squared. So that's what's left over in the numerator. And now if you factor out a copy of h from the numerator, there's a common factor of h in the numerator, we're left with this. And then this h here can be canceled with that h there. And we're left with 2xh. I should remember I've been sloppy. I haven't been copying the limit as h goes to 0 in every line. But remember that we are taking the limit as h goes to 0 of this expression, 2x plus h. So now if you replace the h with a 0, you have 2x plus 0, which is just 2x. So that proves that sure enough, f prime of x is 2x. Now, this is actually kind of a big deal, because here's the thing. If you compute the derivative of this function, and this leads into really what today's lesson is all about. If you compute, and this is what exercise 4 is about, I actually don't think that I'll do all of exercise 4, but I do want to sort of mention the discussion that's in exercise 4. If you compute the derivative at a specific number, like 4, or at 5, or at 6, then you get a number, right? Like the derivative at 4 is 8, which is a number. The derivative at 5 is 10, which is a number. But if you compute the derivative at not a specific number, but at like a general arbitrary unknown value, which we call x, then what you actually get is a function, right? This is a function, not a number, that's a function. So there's kind of a big difference between these two ideas, okay? You can take the derivative of a function at a point, like at a specific number. That's what we're doing here, and you're going to get a number. But if you take the derivative of the function, like not at any specific point, but just at a general arbitrary x, then you get a function, okay? And this leads to the following idea. So the derivative of a function, let's just call it f of x, maybe we can say in general, that is to say, not at a specific point, is another function, right? The derivative, so the example that we did was the derivative of x squared in general, not at a specific point, but at the variable x, like in general, the derivative of the function x squared is another function, 2x. Okay, and this generalizes. This is always true. You can always do this. Given any function, you can apply the limit definition of the derivative, and rather than taking the derivative at a specific point, like 2 or 3 or 4, you can just take it like at a variable x, and what you'll get is another function involving x. So these are really actually two different ideas: derivative at a point versus just the derivative in general. Derivative at a number versus derivative like at a variable. And in practice, we distinguish between these two ideas in the following way. If we mean the derivative at a specific point, like the derivative at 5, we'll say the derivative at 5. But if we mean this idea, if we just mean the derivative of a function in general, not at a specific point, we'll just say the derivative. I hope that makes sense. If we just mean the derivative in general without a specific point, we just won't mention a point. we'll just say the derivative of x squared, not at 5, not at 6, just the derivative of x squared is 2x. So that's how we distinguish between these two ideas, okay? If we want to refer to this concept where we're just taking the derivative in general, we just call that the derivative, not the derivative at a point, but just the derivative, okay? If you actually go through number 4, and the work for number 4 is not easy, and if you couldn't get to the answer, it's not that big a deal. But if you go through the work for number 4, what you find is that the derivative of 4x squared, that's the function whose derivative I ask you to compute, is 8x. Okay. Now, this is pretty interesting because I hope that you can see that there's kind of a relationship between this and this and this and this. It's not totally obvious, but if you notice, 8, of course, is 4 times 2. Like it's the coefficient in front of the expression times this exponent here. This expression here follows that same pattern. X squared can be imagined as like 1x squared, and then the 2 kind of comes down and multiplies the 1. And what you do is you subtract 1 from the exponent. So, maybe, I don't think I'll go through it, but you can show, just as one more example, I won't prove it to you, but you can do it using a limit definition. You can show that if f of x is say 5x to the third, then the derivative of that function, again, this is the general derivative, the derivative not at a specific point, but in general, will be 15x squared. That's what you'll find. And the pattern here is that this exponent kind of comes down and multiplies the coefficient in front, right? So that's 3 times 5, which gives you 15. And then you subtract 1 from the exponent, okay? And this is pretty interesting. And this pattern actually always works. You can prove, sort of using this limit definition, that this always works. And in fact, certainly if you take AP calculus, you'll definitely see a proof of this. We go through it. And you might wonder, like, what usefulness is this? You'll spend a lot of time in calculus learning what are called derivative rules. The idea that the derivative of this function is obtained by taking the exponent down and multiplying the coefficient and subtracting 1 from the exponent, that's a rule. It's called a power rule. I'm going to make it explicit in a second. But the idea is that computing derivatives using limits is a huge pain. Like, it's just a huge pain. I mean, look at all the work that we did, right? Just to find the derivative of x squared, right? And it's a big pain, okay? So what we want really are shortcuts which allow us to find derivatives without having to appeal to the limit definition, right? And so let me just tell you what those rules are. We're going to go over a handful of them today, but they'll allow you to take derivatives of actually quite a few different kinds of functions. So the topic for today really is derivative rules. I mean, these are basically shortcuts for finding derivatives. Okay, so what are the derivative rules? There are a lot of them, and when you actually take calculus next year, you'll spend a lot of time learning these different rules. I'm just going to give you a few of the most basic ones today. Okay, so first of all, we have the sum and difference rules. Okay, here's what the sum and difference rules say. And throughout this whole discussion, let's let f and g be functions. I don't care what functions they are. Maybe one of them is x squared and the other one is x to the third. I don't care, but just let f and g just be any functions you want. Then here's the sum rule. It says the derivative of f plus g is actually the derivative of f plus the derivative of g. Right, remember this prime symbol really means derivative. So like, just to kind of be clear about what this is telling you, it's saying that, you know, if f and g are functions, then you can add those two functions together to get a new function, right? And you can then ask, what is the derivative, the general derivative of that function? And this rule says that adding the two functions together and then taking the derivative is the same thing as just taking the derivative of each of those two functions and then adding the result. Or alternatively, it says that taking derivatives distributes over addition. The same thing is true for subtraction. If you have one function minus another function, you can ask, what's the derivative of that, right? Because one function minus another, like x to the third minus x squared, is itself a function. And you can ask, what's the derivative of that function? The answer is, it's just the derivative of the first function minus the derivative of the second. So derivatives distribute over addition and subtraction, okay, which is really good. It makes our lives a lot easier. There's something called the constant multiple. The constant multiple rule. And what I'm going to do is I'm going to let k be a constant. Okay, a constant just means a number, like 2 or 3 or 12, as opposed to a function. So here's what the constant multiple rule says. It says the derivative of kf is k times the derivative of f. And that's a little hard to process. This rule, I think, is pretty hard to see, like in practice, or it's pretty hard to see in the abstract what this rule is telling you. In practice, it's a pretty simple idea. But basically what it's saying is, you know, if k is a number like 2 and f is a function, you can multiply that function by that number. Like you can multiply a function by 2 and you'll get a new function. And you can ask, what's the derivative of that new function? This rule says the derivative of that new function, it's the same thing as taking the derivative of the original function and then multiplying by the number. So it's kind of like saying you can either multiply by the number and take the derivative afterwards, or you can take the derivative first, then multiply by the number, and it doesn't make any difference. Put another way, this basically says that constant multiples can just be kind of ignored when you're taking derivatives. They just kind of sit there. If there's a constant multiple sitting there before you take the derivative, it's going to be sitting there afterwards. So 2 more rules. The constant function rule. So again, let k be a constant. So k is like a number or something. Then the derivative of k itself is always just 0. The derivative of any constant function is 0. Conceptually, this makes sense because remember what the derivative is telling you. It's talking about the instantaneous rate of change, right, of the function. And if you have a constant function, like a function that is just always equal to 5, no matter what, that function is not changing. It's not changing at all. So its rate of change is always 0. That's what this guy's saying. Okay. And then finally, the most interesting rule, and this is the rule that I was alluding to a moment ago in the discussion of some of the problems from last time. If we let n be a number, then the derivative of x to the n is equal to nx to the n minus 1. Like, do you remember that the derivative of x squared was 2x? That's an example of this, because, you know, what's the derivative of x squared? Well, this rule says n, which is what the exponent is, comes down and becomes like a multiplier on the side. So 2x. And then you subtract 1 from the exponent. So 2 minus 1 is just 1. So 2x to the 1, but that's just 2x. Okay. So those are the rules that I'm going to focus on today. When I want to make sure that you're not panicking too much, because when we first introduced these rules, people were like, what is going on? I think like this looks incredibly abstract, and it actually is pretty abstract. What you'll see in a moment, though, is that using these rules is actually really straightforward, like really straightforward. In fact, after you use these rules, especially these first few rules, after you've been using them for like a couple of days, you'll forget they even exist. It'll just become second nature. So I know that when you first see this stuff, it's really abstract, but you shouldn't panic. As you're about to see, it's actually really easy. What I'm going to do now is a whole bunch of examples. Okay. I think I'm going to tear this sheet of paper off so I can refer back to it quickly. So what I'm going to do is I'm going to compute the derivatives of a bunch of different functions, okay? Using derivative rules, not using limits, but using derivative rules. So what is the derivative of x squared? All right, that's what this notation means, right? X squared in parentheses with a prime means what's the derivative of x squared? We computed this manually, right? But according to, let's be clear, according to the power rule, all that happens is the 2 comes down, so you get 2x, and then you subtract 1 from the exponent. So that's 2x to the 1, which is 2x. The end. That's the derivative of this function. Okay. Well, how about the derivative of x to the third? Computing this guy with limits is a huge pain. It takes a long time. But with the derivative rule, it's very easy. The power rule says the 3 comes down, and then you subtract 1 from the exponent, which leaves you with a 2. That's it. That's the derivative of x to the third. Okay. Just to be clear about exactly, well, I'll do one more using the power rule just to make sure. So let's give some functions some names. Let's let f of x be x to the fourth. Okay. Then I hope it's clear by this point that f prime, the derivative of this thing is 4x to the third, right? The 4 comes down and you subtract 1 from the exponent. So that's all using the power rule. Like, I just want to make sure before we go any further that we're clear about like what this is actually saying. Like what's really going on here. Here's what this is saying. This, of course, is a function, right? And let's say that you wanted to know the derivative of this function at a specific point. Like, let's say that you wanted to know the instantaneous rate of change of this function here, x to the fourth, at the point, I don't know, let's say x equals 2. Okay, so you want to know what's the instantaneous rate of change of this function at 2. Well, you have a formula for the derivative right here. It says that f prime of x is 4x to the third. I'm asking for the instantaneous rate of change of f at x equals 2. In other words, I'm asking for the derivative of f at 2. And I've got a formula for the derivative, right? The formula for the derivative is 4x to the third. So derivative at 2 is going to be 4 times 2 to the third. I'm just plugging into this formula. So 2 to the third, that's 2, 4, 8 times 4 is 32. That's it. Computing this like derivative using the limit definition is a huge pain. It takes a very long time. But with the derivative rules, it's very, very convenient. So the whole point of derivative rules is that they allow you to compute derivatives without using limits. But you need the limits to derive the rules. Like the limit definition is used to prove the derivative rules. So the way that it goes when you actually take this class next year is you compute derivatives, manually using limits for a long time, but then gradually you begin to prove rules using the limits. And then once you've proved the rules using the limits, you can throw the limits away, is basically the idea. Okay, so let's do, these are all examples of the power rule, right, which was the last derivative rule that I put on here, but there's a bunch of other rules, right, sum and difference rule and so on. So let's put some of those into practice. So let's say that I have, the sum of two functions. Let's say that I want to know the derivative of x to the third plus x squared. What's the derivative of that function? Well, the sum rule says that if you've got two functions being added together, all you have to do is take the derivative of each term separately. So that's going to be the derivative of x to the third plus the derivative of x squared. That's what the sum rule says. And what's the derivative of x to the third? Well, we computed that earlier using the power rule. It's 3x squared plus. And then what's the derivative of x squared? Again, using the power rule, it's 2x to the, I mean, you subtract 1 from the exponent. It's technically 2x to the 1, but x to the 1 is just itself. So, and that's the derivative, right? Or what if I said, what's the derivative of, x to the 5th minus x to the 7th? Well, this rule right here says that derivatives distribute over subtraction as well, right? It's just the derivative of the first thing minus the derivative of the second. So that's, 5x to the 4th minus 7x to the 6th, right? I'm just using the power rule on each term separately, right? Because subtraction rule says that I can take the derivative of this guy minus the derivative of this guy, and I'm just using the power rule on each one. So I hope it's beginning to be clear that even though these are pretty abstract, that the problems themselves are pretty straightforward. Okay, well, we haven't, let's do something like this. How about x to the 6th plus, how about just 12? What's the derivative of that function? Well, again, we can take the derivative of each term separately. That's the sum rule, right? So it's the derivative of this guy, which is, of course, 6x to the 5th, right? The 6 comes down, you subtract 1 from the exponent, plus, and then the derivative of this guy. What's the derivative of 12? Well, you might remember this guy here, the constant function rule. The derivative of any constant is 0. In other words, the derivative of any term which doesn't have a variable at all, like this one right here, is in fact just 0. Okay. So in other words, that's just 6x to the 5th. That's the derivative. Okay. Okay, there is one more rule that we still haven't used, and it's the constant multiple rule. And I'll show you what that means. Let's try the derivative. What's the derivative of the function 3x to the 7th? Okay. Now, what you'll notice here is that this function is not just a power of x, right? Like, yes, there's an x to the 7th here, but there's also a constant multiplying the function in front. There's a constant multiple, the 3 right in front. So it's not just x to the 7th, right? It's 3 times x to the 7th. So how do you use this rule? What this rule says essentially is that when you're taking derivatives, if you have a constant multiple in front, like a coefficient, then you can just ignore the coefficient. It just comes along for the ride. Like, you don't do anything with it. Instead, what you do is you just copy the 3 down, and then you focus on taking the derivative of the rest of the function. Like, in other words, the 3 is just going to come along for the ride, and all you really have to do is take the derivative of the non-constant portion of the function. You have to take the derivative of x to the 7th. And what is the derivative? And that's what I mean here. That's the derivative of x to the 7th. So what is the derivative of x to the 7th? Well, so I've got this 3, right? I'm just copying that 3. And the derivative of x to the 7th is 7x to the 6th. And then I've got 3 times 7, so that's just 21 x to the 6th. Okay. If you look at where I went, from the beginning all the way to the end, you can kind of see that all that happened is the exponent comes down, multiplies the number in front, and then you subtract 1 from the exponent, right? Let's do another one like that. So something like, how about 5x to the 4th? Okay, what's the derivative of that function? Well, I'm not going to go through the whole argument here, but basically the 4 comes down and multiplies the 5, that gives you 20. And then you subtract 1 from the exponent. So 20x to the third. It's that easy. Like, it's really that easy. So let's put it all together into a more complicated function and take the derivative. How about the derivative of the function 7x to the third plus 2x to the fifth minus 8. Okay, what's the derivative of that? Well, you just need to take the derivative of each term separately, right? The sum and difference rules say that the derivative distributes over plus and minus, so you just need to take the derivative of this and this and this separately. Okay, so what's the derivative of 7x to the third? That's just like the problems that we just did. The 3 comes down and multiplies the 7, that's 21x, and you subtract 1 from the exponent, so 21x squared. Plus, and then here, taking the derivative of this guy, the 5 comes down, multiplies the 2, that's 10x to the fourth. And then the derivative of, negative 8, that's a constant, right? The derivative of a constant is 0. So, you can write like minus 0 if you want, but that's not really doing anything. The derivative is just 21x to this x to the second plus 10x to the fourth. Okay. How about, here's another one. How about, what's the derivative of just x? I mean, x is itself a function. It's kind of a silly function, but that's a function. And what is its derivative? Well, you can actually use the power rule to get the answer, because you can write x as x to the 1, right? I want to be clear. This is a prime. This thing on the outside is the prime symbol. It's like the apostrophe that means derivative, and this is a 1. So what I'm saying here is that x can be thought of as x to the 1. So when you take its derivative, you can use the power rule, right? It's like x to the power of something. So what does the power rule say? It says the 1 comes down, so you get 1x, and then you subtract 1 from the exponent, leaving you with 0. So 1x to the 0. Okay, that's what you get according to the power rule. Now, x to the 0, though, anything to the 0, if you remember your exponent rules, hopefully you do, anything to the 0 is 1. So this is actually 1 times 1, which is just 1. So the derivative of x is just 1. Okay. Okay. To show you the power of this, I think I want to go back. I'd like to go back to an exercise that we did a long time ago when we first started talking about instantaneous rate of change. If you remember, we did a problem involving a rocket, okay, in class. And if you remember, this is maybe day 3 or something, I forget, day 4. We had a rocket and its height was given by this function right here, 90 plus 64x minus 16x squared, okay? And the problem was asking you, what is the instantaneous velocity at 1 second into the trip? If you remember that, what is the instantaneous velocity 1 second into the trip? That, of course, is the same thing as asking what's f prime of 1? Like, what's the instantaneous rate of change 1 second into the trip? That's what this was. And here is my work. Here's the work that I did, like, on camera. Here I am using the first limit definition, right, of the derivative. And I'm sort of plugging like everything in, and I eventually get 32. Okay, but it's a lot of work. All right. So, how long would this problem take if I were to do it using derivative rules? Okay. A lot less time. Right. So here's the function, right? That's the rocket's height. And you want to know how fast is it going 1 second into the trip. So all you need to do is use derivative rules to find a formula for the derivative, like in general, right? So what's the derivative of this function? Not at 1, but just in general. I want a formula for the derivative, right? And ultimately what I'm going to do is I'm going to compute f prime of 1, but start by finding a derivative of this expression. So the derivative of 90 is 0, because it's a constant, plus the derivative of 64x, well, you know, let's think about that. What is the derivative of 64x? We said that the derivative of x is just equal to 1, right? And remember what I said about constant multiples? The derivative, if you have a constant multiple like 64, then you just kind of ignore the 64 and take the derivative of this thing right here. And we said that the derivative of x is just 1. So the derivative of 64x is actually just 64. And then minus 16x squared, well, the derivative of that, you know, the 2 comes down, you get negative 32x. So the derivative of this function in general is 64 minus 32x. And then if you want to know what's the derivative specifically at 1, you just plug 1 into this function. F prime of 1 is 64 minus 32 times 1, which is 32. That's 2 lines as opposed to this. And, you know, and now that I've already got a formula for the derivative, I could find the instantaneous rate of change, the instantaneous velocity of the rocket at any other time really easily. Like, what's f prime of 2? That means, like, how fast is the rocket going 2 seconds in? All you have to do is plug 2 into this function. 64 minus 32 times 2 is actually 0. It's because the rocket's actually turning around 2 seconds into the trip. So it's like traveling at 0 miles per hour right at that moment. So, you know, and if you want to know f prime of 3, very easy. You just plug 3 into this thing. 64 minus 32 times 3, which is, I think, negative 32, right? So very easy to find, as opposed to, you know, without the derivative rules, you have to crank through this whole thing for every single one of these guys, right? So it saves a huge amount of time. Obviously, this is a huge time-saving device. I think that, you know, what I'll do is just a couple more examples to kind of help you with the exercises in today's worksheet. So first of all, I think it's worth, you know, reiterating. I think that it's probably worth reiterating just one more time. What if I want to know the derivative of, like, 72x? Okay, what's the derivative of that? Well, you can view 72x as, you know, well, let's put it this way. The 72 can be ignored by the constant multiple rule, right? You can just pull it out. And so that's 72 times the derivative of x, right? And we showed a moment ago that the derivative of x is just 1. So that's 72 times 1, which is just 72. In general, the derivative of something x is just the thing, right? Like if I ask you, what's the derivative of 64x? The answer is 64, right? That's what I was doing up here in the previous problem. If I ask you, what's the derivative of 35x? It's just 35, okay? So the power rule, you know, which tells you how to find the derivative of functions like x to the n, x to some power, can actually be used for lots of different kinds of functions, because lots of functions can actually be written in this way. And I'm just going to give you a couple of examples. How about, what about the derivative of the square root of x? What's the derivative of that? Well, the trick here is to recognize that the square root of x can be written using a fractional exponent. The square root of x is the same thing as x to the power of 1/2. And so I can use the power rule to find the derivative of x to the 1/2, right? The 1/2 comes down. And then you subtract 1 from the exponent, leaving you with negative 1/2. So that's the derivative of this function, okay? Or how about this example? How about the derivative of the third root of x? Well, the third root of x can be written as x to the 1/3. And if you want to take the derivative of that, well, you can use the power rule, right? The 1/3 will come down. And if you subtract 1 from the exponent, 1/3 take away 1 is negative 2/3. So that's the derivative of the third root of x. So you can see that, root functions actually can be, you can use the power rule on them because root functions are really just, fractional exponent functions. Or how about a problem like this? What about the derivative of say 1 over x to the 4th? I want to be very clear, you may not simply take the derivative of the top and the bottom of this fraction. That doesn't work. Derivatives don't distribute over division. They don't. But what you can do is you can say, well, 1 over x to the 4th is the same thing as x to the negative 4. And then I can use the power rule, right? The power rule says that the negative 4 comes down, and I subtract 1 from the exponent. That gives me negative 5. So that's the derivative of that function, right? Yeah, and maybe just one more like this. Let's do a really tough one, and I think I'll stop there. What about the derivative of 7 over, say, the 4th root of x? What's the derivative of that function? Well, you have to rewrite this function quite a lot, but if you rewrite it in the right way, then you'll eventually be able to use the power rule. So this is the same thing as 7 times 1 over the 4th root of x, okay? Just take a moment and convince yourself that that's true. Right? 7 times this fraction, the 7 just multiplies the numerator, right? So this is just rewriting this function here. And then the constant multiple rule says, hey, 7 is a constant multiple, you can just ignore it. So the 7 will just come along for the ride, and all I need to do is figure out the derivative of this portion here, right? And how can I figure out the derivative of this thing? Well, 1 over the 4th root of x can actually be written using a negative fractional exponent, okay? Because, first of all, maybe I'll do it in 2 steps. The 4th root of x is the same thing as x to the 1/4. And then 1 over x to the 1/4 is actually the same thing as 7x to the negative 1/4. And now finally, I'm in a position where I can use the power rule, right? Because I'm taking the derivative of a function that is of the form x raised to a number. So the power rule says that I bring the exponent down, so 7 times negative 1/4, and I subtract 1 from the exponent, negative 1/4, take away 1 is negative 5/4. And so this is the derivative, it just maybe needs to be cleaned up a little bit. 7 times negative 1/4 is the same thing as negative 7/4 x to the 5, negative 5/4. Okay.